horizontals. The sides will be the outer converging lines. The unrotated square is revealed. Once the square is drawn, the corners of the rotated square can be connected. The corners for the rotated square are easy to find in this example because the square is at 45 degrees. But placing the corners of any other degree of rotation is just as simple. Draw the bounding box around the rotated square, and where those intersect the diagonals, draw lines across the orthographic plan or recede into the distance. Then, working in reverse, the corners can be found on the perspective plane. This process can be seen in the other screen captures of the cubes drawn in this video. Wherever the corners or vertices of the rotated square are, a horizontal line or a line parallel to the edge of the orthographic plan is drawn. Where this horizontal intersects either line, that belongs to the width of the unrotated square in perspective. The width at this depth is used to mark or measure the height of the corresponding leg or edge of the rotated cube. Once the edges are drafted, they can be joined to create the top face of the cube. The rear edge is extruded to the right. A plan is then carried out in the same manner as before. The same general process and idea is used. The heights for the new right edge are again taken from widths of the unrotated square on the bottom plane, the Y plane, that coincide with the location of the new edges. The additional height of the rotated square is taken, and a rectangle of the same height with sections marking the height of the unrotated square is scaled to match the height of the unrotated square or cube as it's placed near the viewer in perspective. Anytime this method is applied in this example, it is more tedious than the process would be in traditional or physical art due to the limitations of working in software. In some cases, software designed for geometry is necessary or at least easier to use, when in physical art the process is quick and easy, especially if the artist has a compass pair or equal space divider, although a piece of scrap paper and a writing utensil works just as well. Now that the rectangles are scaled and placed, the outer vertices and inner sections can delineate the convergence for this side of the rotated cube. Circles or dots are used to make snapping lines to spots easier and to facilitate division of vertical and horizontal segments. They are used, for example, to divide the edges of the first cube rotated on the y-axis in halves, therefore indicating the half or midline, which with a diagonal can be used to find halves at 90 degrees. This is another process that is much easier and faster with physical media. The right face of the cube is divided with lines that will extend to meet the converging lines on this side. Then the rectangles marking the heights used to point out where the limits of the diagonals will be, so the new rotated face can be drafted. The heights indicated by the rectangles on the right side of the cube are transferred to the left in order to mark the new heights where they intersect the vertically extended edges of the y-plane rotated cube. With these plans in place, the rotated face is drawn. Heights from the rear orthographic plan are translated across the left. Any of the vertical or horizontal metrics can be transferred vertically or horizontally, or more accurately, parallel or transverse to the orthographic plan of origin. First, the heights and any other marks are moved, then the same process is performed to denote placement of the new side. Once the new rotated sides are drafted, they are married with interconnecting lines. All that is left is some rendering and the cube is complete. With cubes on an Inkscape, using the bottom-up method, there are no lines pointing to a vanishing point that miss the mark, not even in the slightest. This can more easily be accomplished with physical art. Finally, a comparison between cubes in the same rotation using Blender. Overall, there are some differences, occasionally minor, which a portion of will be due to how Blender handles objects, which includes Blender adding a third vanishing point when the drawing does not have one, some due to the variation in precision as well as other variables. The Blender examples were made using a 50mm lens for the field of view. When this metric was changed, the main difference seemed to be that the scope would change. In other words, more or less, objects might fit in view. When this is changed in drawing, the amount of distortion also changes, similar to an actual lens. This could also account for some discrepancy. Here's an example of rotating from global or local rotation. This is similar to the idea mentioned earlier about the difference between rotating the camera or view instead of the object. Here is a drawn example of this difference. In many or most situations, this is the contrast between what I term rotating the view in comparison to rotating the cube or object. As I mentioned at the beginning, the old drafting methods often would lean more towards rotating the object, and today most are in the vicinity of rotating the view instead. Neither is entirely true, since both approaches are capable of the other in some way, not to mention that there is a vast array of methods in any direction. When drawing a cube, as in the example on the left where the view rotated for the x and z axis and the cube is rotated on the y axis, the whole grid with all three horizons can be rotated, centered on the cone of vision to get cubes rotated on the other two axes. That's to say, the view is rotated. Another point that can be demonstrated with Blender is the difference between rotating a cube using a global compared to a local or normal gimbal.